This presentation is the first of 3 presentations discussing properties of the Laplace transform. Now you may be asking yourself, why are we going to spend so much time discussing the properties of the Laplace transform? These properties will turn out to be critical to doing much of the analysis that we'll do throughout the class. The first of these properties you already know. It's the linearity property. If you don't recall it, you should review the last presentation. So now let's discuss our second property, the time shift property. And it says the following, that if we have a signal x of t, whose Laplace transform is called x of s, then the Laplace transform of a delayed signal x of t minus cap t is equal to e to the minus s cap t x of s. Now the original signal x of t must be causal. Otherwise we couldn't do the unilateral Laplace transform in the first place to get x of s. So what does this property say? It says if we have the Laplace transform of some signal and we wish to find the Laplace transform of that signal delayed by cap t, all we need to do is to multiply the Laplace transform by e to the minus s cap t. Let's do an example to show the usefulness of this result. We'll find the Laplace transform of the following signal. You'll note that x of t starts at time 1, it ramps till time 2, then it's constant till time 4, and then it's 0 after time 4. We can break this signal up into the sum of 3 signals. x1 is a ramp that starts at time 1. x2 is a negative ramp that starts at time 2. And x3 is a negative step that starts at time 4. When we add these 3 signals together, we will produce the original signal x of t. We write this result here. X of t is a delayed ramp starting at time 1 minus a delayed ramp starting at time 2 minus a delayed step starting at 4. In terms of a mathematical expression, it's t minus 1 u of t minus 1 for the delayed ramp starting at time 1, t minus 2 u of t minus 2 for the delayed ramp starting at time 2, and u of t minus 4 for the delayed step starting at time 4. All of this just from the time shift property. Now, since the Laplace transform of the ramp t u of t is 1 over s squared, and the Laplace transform of the unit step u of t is 1 over s, we can now find the Laplace transform of x of t using the time shift property of the Laplace transform. Note that we obtained the Laplace transform of the ramp and the step from a Laplace transform table. Recall again the shift property of the Laplace transform. It said that if we had the Laplace transform of some signal x of t, and it was called x of s, and we wanted to find the Laplace transform a delayed version of x of t, we simply needed to multiply the Laplace transform x of s by e to the minus s cap t, where cap t is the delay. We'll now use that result to find the Laplace transform of the expression we had on the previous page. We find x of s is e to the minus s times 1 over s squared minus e to the minus 2s 1 over s squared minus e to the minus 4s 1 over s. Recall that 1 over s squared corresponds to the ramp, and e to the minus s will correspond to a delay of 1 second. E to the minus 2s corresponds to a delay of 2 seconds, and e to the minus 4s corresponds to a delay of 4. 1 over s is the Laplace transform of a unit step. So altogether, this expression gives the Laplace transforms of x1, x2, and x3 as the three terms shown here. This example illustrates how the shift property of the Laplace transform can be used to find the Laplace transform of complex signals. We'll close this presentation with our third property of the Laplace transform, and this is the frequency shifting property. It says the following: if the Laplace transform of x of t is x of s, then we may find the Laplace transform of x of t multiplied by an everlasting exponential in the following fashion. The Laplace transform of x of t e to the s0t is capital X of s minus s0. That is, we simply replace the argument s in x of s by s minus s0, where s0 is a fixed value. For example, consider the Laplace transform of u of t. It is 1 over s. What if we wish to find the Laplace transform of e to the at u of t? You note this looks just like u of t, except it's been multiplied by the everlasting exponential e to the at. What we need to do is to replace the occurrence of s in the Laplace transform of u of t by s minus a, where a is taking the role of s0. Therefore, the Laplace transform of e to the at u of t is equal to 1 over s minus a. We've now finished overviewing the first three Laplace transform properties. In our next lecture, we'll continue this investigation.
Work all day, work all night, trying to get problems right. Your worst fears have come true. Yes, you need to convolute. Your face turns red, you get all sweaty, and you cry out, how? But there's a way that you don't know. What does Laplace say? E to the negative st, x of t dt to infinity, e to the negative st. What Laplace say? E to the negative st, x of t dt to infinity, e to the negative st. What Laplace say? Time domain is lame. Time domain is lame. Time domain is lame. Frequency domain. Frequency domain. Frequency domain. What Laplace say? You can find h of t or b both stability. Differential equations. With Laplace the fun begins. Your hair is white, so intelligent, like an owl in human form. But if you meet a nasty function, is integration still okay? Yes. Yes, it is. But is there a faster way? What does Laplace say? Turn to page 344. Use the table to do your transform. Turn to page 344. What Laplace say? I can't integrate that. I can't integrate that. I can't integrate that. That is okay. You don't have to. You don't have to. You don't have to. What Laplace say? Hotty hot ho. Hotty hot ho. Hotty hot ho. Pierre Simon Laplace, ancient mystery, a genius of math and astronomy. You thought about black holes, pretty smart for a French guy, and now we can use your transform. cannot be? Why is there a goblin hiding in the gear? I guess we'll never know. I want to know. Laplace was a boss.